Hey, I think we're going to start. Welcome. Good evening and welcome, everyone. My name is Judy Scamato, and I am the Assistant Director here at Perrott Memorial Library. Tonight, Perrott is pleased to welcome Dr. Emily Mason, a research scientist at Predictive Science, Inc. Dr. Mason will tell us all about the annular solar eclipse that is scheduled to take place this coming Saturday, October 14th. After Dr. Mason's presentation, we'll open things up for Q&A. So please jot down any questions you might like to share at that time. During Dr. Mason's talk, we will all be muted to cut down on background noise. Also joining us tonight is Jen Mankey from Greenwich Point Marketing, and Jen is going to make sure everything runs smoothly. So welcome, Dr. Mason.
Hello, thank you, Judy. Welcome, everyone. I am here to talk about the annular solar eclipse this weekend. So let's get into it. Then we're going to talk about a few things. First, we're going to cover what is an annular eclipse, how is it different from what we think of as a normal eclipse, why they're impressive, because there are some very neat things about even the fact that we have eclipses. We'll talk about where it's visible and how much of it will be visible, because that changes depending on where you are, what you would expect to see depending on where you are, and how to safely observe the eclipse. Because even rules that you might have heard about for total solar eclipses, some of them are different. You have to be a little bit more careful with the annular eclipse. So we'll talk about all of that and then get into ways to get involved in the whole eclipse experience. So I'm going to start with an introduction to the sun. I promise this is the most technical this talk is going to get. So over here on the right, there is a diagram of the sun, and the sun, much like the Earth, has layers, including a core, but the sun's core is a lot different than the Earth's. At the core of the sun is nuclear fusion going on. The sun is a gigantic ball of hydrogen gas, basically, that is so hot that at the core you get nuclear fusion, and that produces all of the other elements that make planets and everything else in the universe. Basically, all of us and everything on the planet was made up during a star's lifetime in its core, either during its life or as it ended its life as a supernova. So the core is incredibly hot. Outside of the core, in this region with kind of the little spiky lines coming out, that's called the radiative zone. And that is a very, very hot region where basically all of the plasma, the gas that was generated in the core, is desperately trying to get away from the core because it's really hot. And that tries to get out and bubbles out until it reaches what we call the convection zone. And this zone basically acts just like a pot of boiling water on your stove. It's really hot at the bottom of that region and it's cooler at the top. So as the hot plasma goes up to the top, it cools off, it gets to expand a bit, and it goes, and then it becomes denser and it starts to sink again. And then it gets down near the bottom, it gets heated up again. So you get these convection cells, these cycles of plasma, and that goes all the way up to just under the visible surface of the sun. Then you have a few different layers that are basically make up the outside skin of the sun in some sense. And those are called the photosphere and the chromosphere. They're very close to each other. What we call the surface of the sun is really just where that huge ball of gas becomes the transition where it becomes transparent at visible wavelengths. So when we first started looking at the sun, carefully shielding our eyes, what we saw as the outer part of the sun we called the surface, but really there's no difference between the layers under the surface, what we called the surface, and the atmosphere beyond that. You just have less and less dense gas as you go out. And then you have the sun's atmosphere above that, which is called the corona. And one of the most amazing things about the sun is that the core, the hottest part of the sun, and the corona, the atmosphere, are about the same temperature, while all of the levels in between are cooler. Sometimes much, much cooler. The surface of our sun is only a few thousand degrees, but the core and the atmosphere are millions of degrees. And we don't know why. So that's one of the driving, like, open questions behind solar physics. And it's one of the things that's driven the field for decades as we try to piece together why the atmosphere is so hot when it's so much further away from the source of most of the energy in the sun. And when we say it's huge, the sun is huge, it really, really is. There's a reason why it's one of the only things in the sky that you can actually see as a disk instead of a point. It is so big and so close. 1 million Earths could fit inside the sun. That's how much bigger the sun is than the Earth. In fact, if you added up all of the mass in the entire solar system, all of the planets, all of the minor planets, all of the asteroids, all of the comets, everything that makes up the mass in the solar system and the sun is 99% of the mass in the solar system. All of the other planets and everything else in the solar system are basically grains of sand. So that's the basic lowdown on the sun. So let's move on and start talking about what happens when you can't see the sun. And I'm gonna play oh right, sorry. So we've been looking at eclipses for a really long time as humans. The ancient Chinese, ancient Indian, Babylonian, Greek, Mesoamerican, all of these cultures have recordings of eclipses, either in cave paintings, like you can see up here in the top right. This is one of the earliest recorded images of an eclipse. This is in Chaco Canyon. There's carvings from the Babylonians. There's all different things. The ancient Egyptians have things that might have been eclipses depicted in some of their like friezes and carvings. Everybody recorded eclipses, and there's some evidence that some of the cultures could actually predict them. And as we got better at predicting them over time, by the 1800s, this had kind of become an early extreme sport. It was kind of the founding of eclipse chasing, where the gentlemen scientists, the ones who were independently wealthy and spent most of their time investing developing early modern science, would be able to predict where an eclipse was and where the path lay of the longest period of the sun being covered. Because it doesn't just matter where you are on the Earth for being able to see the eclipse or not, it also matters for how long the eclipse is going to last from that location. And they would figure out where the best place was. And sometimes it would be halfway up a mountain in the Himalayas. Sometimes it would be out in the American Midwest. Wherever it was, they would go trek out there and try to observe it and make as many measurements and as detailed observations as they could across those precious few minutes of totality. And this actually is a fantastic example of that. This is an image of the eclipse in 1878. And this was taken from the summit of Pikes Peak. And people very nearly died at Pikes Peak trying to see this eclipse, including one of the founders of modern meteorology, and the founder of the National Weather Service, climbed up this mountain, which was getting hammered with awful storms and snow and everything, even though it was in July. And people risked life and limb to be able to make these drawings. The 1919 eclipse helped support Einstein's special theory of relativity, because while they could see like the night sky during the day basically, and they could see how the path of a star's light bent around the path of the eclipse, which it bent due to the sun's gravity. And that helped prove the special theory of relativity, that very massive objects could bend light around them. So that was a critical turning point and one of Einstein's like great moments of being vindicated. And all the way up to now, I mean, now we have images like this that are composites. The center part is ultraviolet light imagery of the sun at that time, and surrounding it is a beautiful, very highly edited, stacked image of what the eclipse looked like from, I think this was Seattle in the 2021 eclipse. We've come a long way, but we're still looking at eclipses. And the 2017 eclipse was one of the first to have broad citizen scientist support. And that was absolutely fantastic to see more and more people getting involved and participating in it. And we have way more planned for the 2024 eclipse, the one that's coming in April. So now I'm going to play a short video by NASA about how eclipses actually physically happen with the alignment of the Earth and the Moon and the Sun. And then we'll talk about it a little bit in more detail. So sit back and relax, and I'll be back with you in a minute.
Roughly every year or two, somewhere in the world, the sun appears for a few moments as a ring of fire in the sky. This is called an annular solar eclipse. Annular comes from the Latin word annulus, which means ring. An annular solar eclipse occurs when a new moon passes directly in front of the sun but appears too small to cover it completely. But why is that? It's because the moon's orbit around Earth isn't a perfect circle, but rather an ellipse, or slightly oval-shaped. This causes the moon to move closer to us and then farther away during its month-long orbit. When the moon is at its closest point, called perigee, it appears slightly larger in our sky. When it's farthest from us, at apogee, it appears a little smaller. But we don't see an annular eclipse every month. That's because the moon's orbit is also slightly tilted in relation to Earth's orbit around the sun. This means during most months, the moon is either too high or too low to block the sun. So only when a new moon is at apogee and passes directly between Earth and the sun, do spectators on Earth get the rare opportunity to see the ring of fire in the sky. Unlike a total solar eclipse, when the moon completely covers the sun, during an annular eclipse, the sun never fully disappears. So if you're lucky enough to be in the path of an annular solar eclipse, make sure to wear your solar eclipse glasses or use other safe solar filters to witness this spectacular ring of fire in the sky.
Okay, so that was a good intro to what is an annular eclipse, but I want to zoom out for a minute and talk about how amazing it is that we even have eclipses, solar, total or annular, to begin with. So we live in a time period and on a planet that has a minimum of 2 solar eclipses per year. And you figure our sun's an average star, we're an average planet, we probably have an average moon, so that it must be fairly common to get eclipses, right? But to get an eclipse, you need a lot of things, and you need a lot of things to line up. You need to have a moon to begin with. Not every planet has a satellite. There are planets in our solar system and outside that just don't even have a moon. You won't get an eclipse if you don't have a moon. The moon needs to be round, which seems simple, except when you think about things like this image over here, which is an actual image taken by the Perseverance rover of Phobos, one of Mars's 2 moons, eclipsing the sun. And you can see Phobos is not round. Both of Mars's moons, Phobos and Deimos, are captured asteroids. So they're just lumps of rock that orbit Mars. So you're not going to get as impressive an eclipse with something like that, where you just have this kind of chunk of rock casting a faint shadow as it goes across the surface of the sun. In addition to that, the moon has to orbit at the right distance so that it appears to have the same size as your star. And this is why I say that we live in a time when we have these solar eclipses, because our moon is moving away from us a few inches every year. So there was a time when the moon appeared bigger and would have completely blotted out the sun during an eclipse. And there will be a time in the future, I believe it's several billion years from now, where the moon will finally be so far away that it will never be able to create a total solar eclipse again. So we're living kind of in this golden era where you actually get both annular and total eclipses at different times. And the last thing that you need, this is a little complicated, is that the orbital plane of the moon has to be close enough to the solar system's orbital plane so that all three bodies can align. And that part's a little technical, so let's talk about that a little bit more. Let's talk about syzygy. It is more than just a great Scrabble word. A syzygy is any straight line alignment of three or more celestial bodies. So that can be the sun, other stars, planets, moons, comets, whatever. You just need three things in space that line up in a straight line. And a special type of syzygy is an eclipse. So over here in this image, you've got the sun at the center. This blue oval is the Earth's path. And then going around that is the gray oval, which is the moon's orbit around the Earth. So the Earth goes around this way, around the sun. And as that's happening, the moon is looping the Earth every month. So this is how you need these things to line up. The position of the moon tells you whether you're going to have a lunar eclipse or a solar eclipse. If the moon is between the Earth and the sun, you get a solar eclipse. If the moon is behind both the Earth and the sun, you get a lunar eclipse because then it's the Earth's shadow that's covering up the moon. So that's how you decide which kind of eclipse you're going to have when all three line up. But most of the time you have the moon either the tilt, the 5-degree tilt, it's so little, the 5-degree tilt of the moon's orbit means that most of the time as the moon orbits the Earth, its shadow either passes over or under the planet entirely. That's why you don't get an eclipse every month. So that you can see in this image that why you don't get the eclipse every month. And what determines whether the eclipse, when you do get a solar eclipse, whether it's annular or total, has to do with whether the moon is at perigee or apogee, like they described in the video before. So if you have the eclipse when the moon is between the Earth and the sun, so you get a solar eclipse, definitely. If that happens when the moon is at its closest to Earth, it appears bigger, it covers the whole sun, you get a total eclipse. If the moon is between the sun and the Earth, when it is really far away from the Earth at apogee, then the moon appears smaller and you get an annular eclipse because it can't quite cover the whole solar disk. So that's the whole complicated story of how you get which kind of solar eclipse and lunar eclipses for free. So what's actually observing an eclipse like what should you be expecting? In a total solar eclipse, I saw the one in 2017, it was amazing. You get this cone of darkness. It's like a curtain that just all of a sudden drops around you out of the sky. And you can still see the line of daylight all around it. You can see the edge of it. It's that small, but it just kind of rushes up at you. It is rushing. It's traveling at about 5,000 miles an hour across the Earth. And it just drops around you. And you get this immediate sense of the vast height of that shadow. The actual distance between yourself and the moon becomes immediately apparent. And you get a breeze that picks up immediately all around you and just kind of swirls around weirdly because you have this sudden temperature gradient. All of a sudden you're in a shadow, it's dark, and the air starts cooling and it's going, what's going on? And so you get this weird breeze swirling around. You start hearing owls and things in the middle of the day because they're waking up going, wait, it's dark, what happened? And for me, it was an intensely personal experience because this thing that I had spent years and years of my life dedicated to studying, all of a sudden I could look up and see the corona, the sun's atmosphere, with the naked eye, just there like an old friend that you haven't seen in person in so long, just waiting there for you to see it directly. It was absolutely incredible. I hate to break it to you, annular eclipses aren't that exciting. I tell you that whole amazing story of what it's like so that you all go see the 2024 total solar eclipse. But this is a great way to kind of learn about it and maybe get to see kind of the dress rehearsal for it. That's how I think of annular eclipses. Because with an annular eclipse, it's not nearly as noticeable. A total solar eclipse isn't even noticeable. If you're walking around during the day and you didn't know that there was an eclipse happening, over 90% of the disk has to be obscured before you even start noticing there's a difference in the daylight. That's how much extraneous light we just get from the sun every day. You can't even tell until over 90% of it's obscured. And even at 99% coverage, which is about what you're at with an annular eclipse, if you're in the path of, it's called the path of annularity, but the path where you see the most of the sun covered up, the daytime lighting just looks like twilight. So it's not as dramatic as a total solar eclipse. Depending on if any of you are planning on traveling to the path of annularity for this, there will be about 2 to 5 minutes of annularity, depending on where you are along the path. And the whole process is about 2 to 4 hours. You get an hour or two of the sun being eaten into before you get the annulus, and then another hour or two before it passes again. So that's what to expect. Here is a map so that you can kind of pinpoint the amount of the sun that you will see a bite taken out of, depending on where you are. Like I said, if any of you are traveling to the path of annularity, you're probably going somewhere between Oregon and Texas. That is where the path is. It's a pretty wide path. And actually, if I zoomed in here, you would see, this is one of my favorite things, you would see that these shapes are not perfect circles or perfect ovals. And that's intentional. That's not bad rendering of the image. The moon's shadow is not perfect because the surface of the moon is not perfect. So the actual path of totality or annularity is shaped in part by the mountains and crevices on the moon, because those affect how much of the sun is actually covered. So that is very neat. Now, you guys are in Connecticut. Unfortunately, that is in the 20% band. So you're going to see just a little wedge taken out of the sun. But how should you see that? Well, we're going to talk about, the next few slides are all about safety now. So you need either eclipse glasses or an indirect method of viewing at all times during an annular eclipse. So during a total solar eclipse, you may have heard that during totality, you can take the glasses off and look directly at the sun. You can, because during a total solar eclipse, the entire sun, the entire disk of the sun is covered up. You cannot do that at any point during an annular solar eclipse. Please don't take your glasses off. We have up here in the top right a GIF showing how to do this for an annular eclipse. You put the glasses on while you're looking down, then you look up and look at the sun, and then you look back down and take them back off. You can never, ever look directly at the sun during any part of an annular solar eclipse, even if you're in the path of the, like, all of the sun being covered. But there are a lot of fun and indirect ways to view the sun. I love these. They are so easy and so accessible. You can either get eclipse glasses, which are easy, but you have to make sure they're like the right ones. But I hear you guys might have access to those already. There's a pinhole camera. This is fantastic because this idea has been around since the 1800s and it still works, and it's still one of the best ways to observe an annular eclipse, particularly if you want an image that's bigger than, you know, a baby's pinky nail. So for a pinhole projector, you take a cardboard box, you make a little cutout, you slap some aluminum foil over the hole, you take a pin, you poke a single hole into the aluminum foil. On the inside of the box, on the opposite side from the aluminum foil, you tape one sheet of printer paper, and then you stick your head in the box. That is all there is to it. The only thing to remember about this is that the direction that you're looking is away from the sun, because the sunlight is coming in through the hole and projecting itself onto it. So just think it is exactly the same as if you were looking at a projector screen in like a meeting room or something. But that's all there is to it. It is easy. You need a cardboard box and some tinfoil and a piece of paper, and you're good. And this one's really fun because it does project it bigger. So you actually get a bigger image than a lot of the other methods. If that is too technical for you, you can do something even easier. You can grab your colander and take it outside and put it on the ground. And you might have to move it up and down a little bit to get the image like at the right point so that it's not blurry. But every single hole in your colander will turn into a tiny image of the eclipse when you look at its shadow on the ground. Every one of those is an image of the eclipse. And I love this one so much, not just because it makes a ton of tiny images, but it makes you realize that every other time you've looked at the shadow of a colander on the ground or on a surface, you are looking at an image of the entire sun. It's round, not just because the colander hole is round, but because it's acting as a pinhole camera all the time. So that's just one of those cool things to think about. And if you want a more techie version, if you scan this QR code, you will be taken to a site where there is an STL file for you to 3D print a little NASA pinhole projector that is shaped like the continental US and has a little hole in it. And you can use that and hold it, you know, above the ground and do the colander trick basically, but with this little gadget. It is cute and fun, and it's 3D printed. So a lot of people enjoy that. So those are a few methods. And a few words of caution. Like I said, I'm going to skip most of the eclipse classes one because you guys already have those. But if you are looking to obtain more of them, don't buy them from Amazon. There's a specific international standard with the number there that they have to be verified from. There's a list at the bottom of the slide with all different verified reliable sources for solar filters of all sorts to look at the sun during an eclipse, not during an eclipse, etc. Regardless of where you get your glasses from, before you use them, just check and make sure they haven't gotten damaged in any way. They're not separating, you don't have a crack in them, you didn't get a pinhole or a hole scratched in the film or anything. If they're damaged, cut them up and discard them so nobody else finds them and thinks they're okay and uses them and hurts their eyes. Please, please, please check your glasses. Very important to save your eyes. For those of you amateur astronomers that might be in the room, I love you guys. I was one of you. That's how I started. Do not trust eyepiece filters. There are a lot of filters out there that claim to be for solar viewing that attach at the eyepiece. That is a great way to melt your internal mirrors. Your telescope's internal mirrors are not meant to take the amount of light that comes from the unfiltered sun. The only kinds of filters that are reliable for solar viewing, you can adapt a normal telescope to be a solar scope very easily, but the film has to be at the entrance aperture so that you cut down all of that light to something decent before it hits your primary mirror. So if you want to get involved, which I hope you do after hearing about this, it's on Saturday. Watch It is a link that is a live stream of the annular eclipse that NASA is doing. Right now, it's just a loop of a past one, but it will be going live for the eclipse on Saturday. So if it's cloudy or you're not in the path or whatever, you can tune in and still participate and watch it with everybody else in the world. Talk about it, sing about it, write about it, draw it, whatever you want to do about it is participation and is great and helps other people learn about it. If you're really enthusiastic, which I hope you are, you can join a citizen science project. Citizen science is kind of poorly named. We're trying to change the name for it because it confuses people. Citizen of where? Do I have to be a citizen? No. Citizen science means citizen as in like a civilian, not an official scientist with a string of letters after their name. That's all it means. It just means people who like science, who want to join and help do science. Most of the projects listed here focus on 2024, but HamSci at least, and I think the Deb Initiative are both doing things for the annular eclipse this weekend as well. But all of these are slated and geared up to get people on board, get them excited, and get them to help us do science for the eclipses. And you can also use NASA's online resources. You do not have to be an expert in solar science. And you can reach out to your local schools, scout troops, nursing homes, youth groups, whatever, anything, anywhere that you can get to help other people learn about and experience the eclipse. That's something that they may never have thought of or anything, but that they would be really enthusiastic to just do or learn about, even for a few minutes. Let's get out there and teach people about the sun. In the end, it doesn't matter how you do it, just go do it. Watch it, talk about it, get involved. It is awesome. That's what I have. And I'm happy to take questions, not just about the eclipse. If people want to know anything about the sun, I'm open for it. So thank you.
Thank you so much, Emily. That was terrific. Wonderful presentation. Does anyone have any questions for Emily? Don't be shy. You can, if you have a question, you can put it in the chat, or you can raise your hand, and we'll unmute you so that you can ask your question. I will take this time to tell you that we have a limited supply of eclipse glasses here at the library. So if you're interested, stop by tomorrow or Saturday morning. I think it's going to be sometime around 1 p.m. That we'll see that little chunk in Connecticut. So stop by, and as long as supplies last, we'll have more for the total eclipse in April of 24. But we have a small amount now. Anybody have any questions? I wondered if, Emily, if I've heard over the years that the sun is dying, you know, and I wondered, is that true? And is, you know, where are we in that process? I mean,
so yeah, the sun is dying, but in the same sense that we're all dying, by inches, hopefully.
Yeah.
The sun is a G2 type star, which means nothing to most people. It's an average size star with an average lifespan of about 10 billion years, and it is just slightly past the halfway point. It's about 5 billion years old. So our sun is middle-aged. It is one of the great things about stars is that they age a lot more reliably than people do. So the sun isn't going to have something horrible happen to it suddenly that we're not expecting. As far as we know, most stars live right up until they use up all of the elements that it has enough mass to keep compressing and fusing new elements for. And in about 2 billion years, the sun will start its actual death process. But even that will take billions more years for it to be like an actual concern for any life on Earth. So it is dying, but very, very slowly, and we have lots of time to figure out a plan B.
Cool. Good to hear. I see a question from Patricia. She's saying and she's right, rain is predicted here in Connecticut on Saturday. Is there much likelihood of seeing anything here?
I mean, if you're gonna have rain, no. But that's what that NASA live stream is great for. You can tune in there and see something unclouded from somewhere. I'm not sure. They probably have multiple locations that people are filming from to be able to get something without clouds. So I would definitely say make yourself a hot drink and pull up YouTube, watch the live stream.
Sounds like a plan. Yes.
That's what I'll be doing.
Yeah, I would imagine schools will be involved. I mean, certainly if not for this one, then certainly for the total eclipse in 2024. Yeah. I noticed in my reading that there isn't another one then for many years after 2024.
So there are a minimum of 2 solar eclipses on the planet every year. The problem is that, we're 70% water on the surface, and where are those 2 tracks? So there won't be another, certainly not a pair like this. And they do come in pairs, like this one where there was like 2017 and 2024. Of like the total solar eclipses that crossed like most of North America and part of Central America. We won't see one of those again for like 150-ish years, but there are other ones that will be seen. I think the next pair are in a handful of years across like the Mediterranean and part of the Middle East or like Northern Africa. So they move around, and for those with the desire and money to travel around, there are many people who eclipse chase now, and they charter cruise ships to like go out into the middle of the Pacific to catch one and everything. That there's like no end to the opportunities if you have the means to see an eclipse basically every year. But yeah, there won't be another pair going across the US for some time. The last ones were in the 1800s. Now we have these, and then it'll be another 150 something years before it happens again.
So grab it while you can.
Definitely.
Yeah. That makes sense. People tend to be very shy when it comes to questions. Anyone else have a question? You can put it in the chat if you'd rather not speak. And I'm happy to read it from there. I'm really glad we recorded this program because some of it is pretty technical, and you have to, I know for me, I'd like to look at it and listen again to try to understand the relationship of where the moon is going around the Earth, the Earth's orbit and so on.
Yeah, if anybody has questions about that, I'm happy to go back to that slide and spend more time on it. It's something that takes a lot of thinking. If I was in person, I would have brought 2 balls and a light bulb, which is an old but excellent way to actually show how it works and the size of the shadow and everything, all of those different components, because it takes a lot of calculation to figure out where one of these things is going to be, how long it's going to be there, and everything. It's a lot of effort, and for us scientists that do actual like measurements and everything during it, there's a ton of work that goes into figuring out where do we think different features will be visible during the eclipse, what should we focus on to take the measurements, all of those different things. My company, Predictive Science, has a long-standing tradition of we do modeling. It's got a hideous name, but it's the modeling of how the gas moves and how the magnetic field shapes the gas on the sun. And we take measurements as close as we can up to the eclipse so that we can run this model to tell people what it's going to look like during the actual eclipse, to try to save people time, basically. So I can actually, we're going to be building a tool this year for the 2024 eclipse, where we're hoping to make it where from a certain select set of like cities across the US, you can pick one and see where the eclipse is going to be in the sky with our current prediction updated daily in it, of what we think it's going to look like. So if anybody's interested in that, I was already planning on sharing the links because obviously you guys can't click on the links in here. I was going to share those with you all so you can post those along with the recording. And then I can send the URL for the prediction, like once we start making it, once that goes live, if anyone's interested.
That'd be great. I think it's really fascinating. Here's another question. When there isn't a solar eclipse, could we wear the eclipse glasses and look directly at the sun on another day?
Yes, absolutely. And in fact, now for the next couple of years is going to be the most interesting time to do that. Most people, they call them eclipse glasses. They're really just sun viewing glasses. You can absolutely use them, and you should use them as much as you want until they break. The sun has something called the 11-year solar cycle. I didn't talk about it because it wasn't really pertinent to the eclipses, but it's a roughly 11-year cycle of activity. So I talked a little bit about magnetic fields on the sun, but basically, because the sun is made up of plasma, which is a gas, but it's a charged gas, the magnetic fields, first of all, it generates a lot of magnetic fields. And second of all, those magnetic fields have a really, really strong effect on what happens in and around the sun, in its atmosphere and inside. And one of the things that happens is because the sun is a ball of a fluid, gas is still a fluid, it doesn't rotate like a rigid ball. So the parts around the equator rotate a lot faster than the parts around the pole, and that twists everything up. So if you think about like a bar magnet, if you ever did that thing as a kid where you had the bar magnet and the iron filings and you could see the loops of the magnetic field going from one end to the other, that's the sun's basic magnetic field. But when you add in the fact that it's doing this rotation that's changing at different latitudes around it, it starts churning those fields up on the inside. And it knots them up into these huge knotted balls that poke out through the surface during time. Excuse me. And those are called sunspots. And you can see them with the eclipse glasses during the active phase of the solar cycle. You can see those. They look like the sun has acne, basically. You can see these spots crop up along like the middle latitudes of the sun, and you can see them come up and move around and go away over weeks. So it's a great time to be using the eclipse glasses to look at the sun, because you'll get to see all these sunspots that are signs that that our sun's magnetic field is chugging away and doing its thing.
Cool. Another question, how would you know when the eclipse glasses have gone bad? Is there a way to check if there is no obvious damage that the glasses are good or not good to use?
You can always hold them up with like a piece of paper behind it. And if you see any light like coming through it, like a crack or something that shouldn't be there, then get rid of them. Other than that, if there's no obvious damage, and that trick with the paper like looks okay, they should be fine.
Cool. And another question, when are times, days to see the sunspots on the sun? What are there best times or days to see them?
No, it's just however many are on the sun right then. Like I said, because we're heading towards what we call solar max, which is a few years where you have the most sunspots on the sun. You have a good shot of seeing some on the sun any day or time. A sunspot takes about 2 weeks to cross the sun as the sun rotates. So once you spot one, it's going to be there for a bit, unless it decays very quickly. They can also emerge very quickly, which is fun because you can be looking at the sun one day and then there's not much there. And then you look the next day and all of a sudden, whoa, there's a spot. So it's really fun to track from day to day. If you want to track whether there are any sunspots before you go out, there's a great website. Actually, there's several, but the best one is called HelioViewer. It's again, helioviewer.org. It is a very, very simple website, and if you put in the AIA 4500 line, into like the little pull down menus on the side. Actually, you know what? I could do a little demo as long as I'm screen sharing. Hang on. Let me stop sharing and pull up the website because I love this website and not nearly enough people know about it. Okay. Okay. If you go to HelioViewer, this is what you will see. Something like this. It probably won't be this image, but you'll see something like this. It automatically loads to today's date, to whatever the newest image is. So it's within a few hours. And if you go to SDO, you want SDO, that's the Solar Dynamics Observatory. And then AIA 4500, you will get okay, maybe 1600's better, 4500's decayed. Okay, 1600. These clusters here, these blotches on the sun are the sunspots. So you can pull that up and see if there's anything interesting. These are probably unlikely to be easily visible. This one might be when it rotates more towards the center, but these are probably too small to see easily with eclipse glasses. But you'll see as the cycle goes on, like if we tune this back to like 2015,
oh yeah.
Of course it's going to make a liar of me. Yeah, there we go. So things like this, where that's like a bigger, darker blotch on the sun, things like this would be easily visible with the eclipse glasses. So you can always check this website before you head out with your glasses to see if there's anything worth looking at.
Very interesting. Okay. I'll just make sure there aren't any other questions that we have missed. Let me just see. No, it doesn't look like it. So before we go, anyone else have any questions? Is there anything else to see? Is there anything else to see at the time of the eclipse?
Oh, like if you can
in
see
the sky
things. So not during an annular eclipse, like I said, because the sun is not quite fully covered. There's still too much just ambient light coming from the solar disk. It still blots out everything. But if you see a total solar eclipse, yes, you can see some of the other bright stars that are out, or planets, during those few minutes of totality. I wouldn't recommend wasting the time like to look at them when you could be looking at the eclipse itself, but if you're interested, you definitely can. One of the fun things about that is that it's the opposite seasons stars. So you only see certain constellations during the year because as we go around the sun, we're pointing at different constellations. But you're always, when we think about the constellations, it's at night. So it's always the stars that are on the opposite side of us from the sun. But during the total solar eclipse, you're seeing the stars that are hidden behind the sun. So you're actually seeing the opposite season's stars, which is fun if you're geeky like me.
Fascinating. Cool. Okay. Okay, I think that That's it for the questions. Emily, it's been fascinating, wonderful presentation.
Thank you.
So grateful for your time and your expertise. And maybe we can have you back next April when we are, if you're not too busy, when we're preparing for the total eclipse.
February or March might be better. I'm part of the prediction effort, and we have to travel to Texas for the eclipse. So
I see. Okay, so we'd have to get you beforehand.
a little bit beforehand would be great, but I'd be happy to come back. Thank you for having me.
That'd be wonderful. Great. Okay, well, thank you so much. And, you know, I look forward to seeing something on Saturday. I'm not sure what, but something.
Great. Thank you.
Okay, take care. Good night, everyone.
Thanks. Bye.
Bye-bye.